In statistics, a rank correlation is any of several statistics that measure the relationship between rankings of different ordinal variables or different rankings of the same variable, where a ranking is the assignment of the labels first, second, third, etc. to different observations of a particular variable. A rank correlation coefficient measures the degree of similarity between two rankings, and can be used to assess the significance of the relation between them. For example, two common non-parametric methods of significance that use rank correlation are the Mann-Whitney U-test and the Wilcoxon signed rank test. Context: if, for example, one variable is the identity of a college basketball program and another variable is the identity of a college football program, one could test for a relationship between the poll rankings of the two types of program. Do colleges with a higher-ranked basketball program tend to have a higher-ranked football program? A rank correlation coefficient can measure that relationship, and the measure of significance of the rank correlation coefficient can show whether the measured relationship is small enough to likely be a coincidence. If there is only one variable, the identity of a college football program, but it is subject to two different poll rankings, then the similarity of the two different polls rankings can be measured with a rank correlation coefficient. Correlation coefficients. Some of the more popular rank correlation statistics include Spearman's rho, Kendall's tau, Goodman and Kruskall's gamma. An increasing rank correlation coefficient implies increasing agreement between rankings. The coefficient is inside the interval -1, 1, and assumes the value 1 if the agreement between the two rankings is perfect. The two rankings are the same. 0 if the rankings are completely independent. -1 if the disagreement between the two rankings is perfect. One ranking is the reverse of the other. Following diaconus, a ranking can be seen as a permutation of a set of objects. Thus we can look at observed rankings as data obtained when the sample space is a symmetric group. We can then introduce a metric, making the symmetric group into a metric space. Different metrics will correspond to different rank correlations. General correlation coefficient. Kendall showed that his and Spearman's are particular cases of a general correlation coefficient. Suppose we have a set of objects, which are being considered in relation to two properties, represented by and forming the sets of values, and to any pair of individuals, say the th and the th, we assign a score, denoted by, and a score, denoted by. The only requirement made to this functions is antisymmetry, so and then the generalized correlation coefficient is defined by Kendall's as a particular case if is the rank of the member according to the quality. We can define and similarly for the sum is twice the amount of concordant pairs minus the discordant pairs. The sum is just the number of terms, equal to, and so forth. It follows that is equal to the Kendall's coefficient. Spearman's is a particular case if are the ranks of the member according to the and the quality respectively. We can simply define the sums and are equal, since both and range from 2. Then we have, now since and are both equal to the sum of the first natural numbers, namely, we also have and hence being the sum if squares of the first naturals equals. Thus, the last equation reduces to further and thus, substituting into the original formula these results we get where is the difference between ranks, which is exactly the Spearman's rank correlation coefficient. Rank B serial correlation. Jean Glass noted that the rank B serial can be derived from Spearman's. One can derive a coefficient defined on x, the dichotomous variable, and y, the ranking variable, which estimates Spearman's rho between x and y in the same way that B serial R estimates Pearson's R between two normal variables. The rank B serial correlation had been introduced 9 years before by Edward Kewtind as a measure of rank correlation when the ranks are in two groups. Kirby simple difference formula. Dave Kirkby recommended the rank B serial as the measure to introduce students to rank correlation, because the general logic can be explained at an introductory level. The rank B serial is the correlation used with the Mann-Whitney U-test, a method commonly covered in introductory college courses on statistics. The data for this test consists of two groups, and for each member of the groups, the outcome is ranked for the study as a whole. Kirby showed that this rank correlation can be expressed in terms of two concepts: the percent of data that support a stated hypothesis, and the percent of data that do not support it. The Kirby simple difference formula states that the rank correlation can be expressed as the difference between the proportion of favorable evidence minus the proportion of unfavorable evidence. Example: an interpretation to illustrate the computation. Suppose a coach trains long-distance runners for 1 month using two methods. Group A has 5 runners, and Group B has 4 runners. The stated hypothesis is that method A produces faster runners. The race to assess the results finds that the runners from Group A do indeed run faster, with the following ranks: 1, 2, 3, 4, and 6. The slower runners from Group B thus have ranks of 5, 7, 8, and 9. The analysis is conducted on pairs, defined as a member of one group compared to a member of the other group. For example, the fastest runner in the study is a member of 4 pairs, and all 4 of these pairs support the hypothesis, because in each pair the runner from Group A is faster than the runner from Group B. There are a total of 20 pairs, and 19 pairs support the hypothesis. The only pair that does not support the hypothesis are the 2 runners with ranks 5 and 6, because in this pair, the runner from Group B had the faster time. By the Kirby simple difference formula, 95% of the data support the hypothesis, and 5% do not support. So the rank correlation is R equals 95, 05 equals 90. The maximum value for the correlation is R equals 1, which means that 100% of the pairs favor the hypothesis. A correlation of R equals 0 indicates that half the pairs favor the hypothesis and half do not. In other words, the sample groups do not differ in ranks. So there is no evidence that they come from two different populations. An effect size of R equals 0 can be said to describe no relationship between group membership and the members' ranks.